I had an unusually good science teacher in 5th grade. Maybe that's why I am now a scientist. I don't know. But she had me rub hands together. She had all of us rub our hands together, real vigorously and hard, and feel how they get warm. And as you know, if you're outdoor on a cold day, you could do this to get warm too. Unfortunately, it works best on your hands. Doing it on other places isn't as easy because our hands are exposed and they're tough. So you can rub it. So what are you doing there? Well, you know, you should be able to understand this now. Heat is the vibration of molecules. When you're rubbing one molecule into another, you're giving it a little bit of a kick. You are speeding up these molecules. This is what friction is. Friction is the rubbing of one particle on another that gives some of the energy of motion into the motion of this molecule. Now, with the friction, of course, you push it a little bit and then it springs back. And so you get the things vibrating. So when you have friction, friction is something you try to get rid of in many cases. Without it, of course, you'd be like ice skating all the time, so you need it to walk. But this friction, now think of how much work it takes to turn all that into this warming of the hands. Now they do feel warm. You're probably warming them up by a couple degrees. The reason you feel it is because it's a very thin layer that's being warmed up. The amount of work that you have to do to warm it up is really quite a bit. I mean, you know, to give an example, if you are, I mentioned to you that you can do a horsepower. Most of you can do a horsepower. You can do it for a few seconds before you drop from exhaustion. Horse can do it all day. But if you run up a flight of stairs as fast as you can, you have, you've done about a horsepower. Now, let me put in some numbers here, just because they're kind of interesting. As I emphasized, I'm not going to ask you to do these numbers, but you should be familiar with them. You should have some sense of them. So you run up a flight of stairs, one flight, as fast as you can. That's about a horsepower. So that's run up is 1 horsepower. Now here's the number you should know. That's about a kilowatt. Kilowatt is like 10 bright light bulbs. So you're burning like 10 bright light bulbs. Now, I'm going to do some things that you don't really have to know. A watt is 1 joule per second. That's a scientific unit. And so a kilowatt is 1,000 joules per second. And there are about 4,000 joules in a calorie. So you've burned a quarter of a calorie in running up that flight of stairs. A gram of chocolate chip cookies is about 6 calories. So if you've used 1/6 of a gram, it's rather amazing, isn't it? How much energy there is in a little bit of food. Of course, you already know that, because you spend your whole day, and how much do you eat in a day? You may be surprised, it's not much. Usually it's not much, it's less than 2 pounds, even if you eat a lot. You don't eat that much food. I first became aware of this when I went backpacking. We had to carry our food. And we learned that a little bit over a pound a day. And that's when you're backpacking. And it's plenty. I'm not including the water. You can drink a lot of water. But if you eat more than that, and you're normal, you'll gain weight. Or gain weight could be growing, which you generally do up until a few years ago. And then if you eat more than that, you grow a different way. But it's still growing. So here, you run up a flight of stairs, and you're using 1 calorie, which is a couple little grains of a cookie. There's a lot of energy in food. A calorie will also raise 1 gram of water by 1 degree Celsius. So I'm sorry, this is a food calorie. Okay, so a food calorie is 1,000 little calories. The difference is, this is a terrible notation, but it has a small c. It's a chemist's calorie. If it's a big C, it's a food nutritionist's calorie. I ran into trouble with that once when I guess I was baking my first cake. I was rather late into the cooking business, and I'd never baked a cake. And my wife, who was a wonderful, intuitive, great cook, was basically being my tutor. So I was going to impress her by baking this cake, so I followed the recipe. Now, she never follows recipes. She has an intuition, but I follow recipes. So at one point it asked for, I think it was 3 tablespoons of baking powder. So, because it asked for 3 tablespoons of baking powder, I put in 3 tablespoons of baking powder. How many people here are chuckling and laughing? See, a bunch of you know that this is not a tablespoon. This is a teaspoon. A tablespoon is this. Oops. With a big T instead of a little t. And somehow you're supposed to know that when you start reading a cookbook. Well, for someone who would question up there. A little calorie will raise 1 gram of water by 1 degree Celsius. The big calorie will raise 1 kilogram of water by 1 degree Celsius. Okay, so this is a good thing to know. I want you to know what a calorie will do in terms of temperature. Now, you have just burned a calorie. You have turned it into heat. Some of that goes to heating you up, not nearly a degree Celsius, because you know a degree Celsius is 9/5 of a degree, almost 2 degrees Fahrenheit. And you know what it feels like to have a fever. So these are the sorts of numbers. But basically it says there's a lot of work that goes into 1 degree. Now, dynamite, when it blows up, has like a little bit less than 1 calorie per gram. 1 calorie per gram. As I recall, it was actually 0.6 calories per gram. That's dynamite. Or let's call it TNT. TNT and dynamite are actually slightly different, but I use them interchangeably as basically our generic explosive. 6 calories per gram. Now, how much would that raise the temperature of a gram of water? Well, these are 0.6 big calories. That's 600 big calories. That's 600 little calories. So that would raise a gram of water to 600 degrees, way beyond the boiling point, turning it into a gas and an explosion. So this is, I want you to rub your hands and actually feel this and get a sense. Now, there is water. Everything is at room temperature. These molecules are moving. You remember the velocity at which they move. They move at approximately the velocity of sound. The big molecules will move slower. The little molecules will move faster. They all have the same energy. The energy of well, there are different units for that. You don't have to know what that energy is. The equation relating energy, the average energy of a particle to the temperature, let me just write it down in a different form. Last time I wrote that the energy of an individual molecule is the energy of motion. This also could be energy in spin also. Could be energy in vibration. We're not counting that. This is just kinetic energy, energy of motion. And this is an equation you don't have to know. 2e to the minus 23 times the temperature Kelvin. This can also be written as 2 times 10 to the minus 23 TK. Some people who have actually studied advanced math ask whether this E is the E that's used in calculus. The answer is no. This is just calculator notation. It stands for 10 to the minus 23. And we could, put TK on the other side, and we say that the temperature of an object is equal to 5 times 10 to the 24th times the energy of a molecule. Wow. That's a big number. Well, the molecules are really pretty tiny. Okay, so if you want this to be 300, you'll get that the energy of the molecule is really, really tiny. But they are tiny. You don't feel molecules. The thing, when you feel heat from something, it's because it's not individual molecules that are hitting you, but because there are so many of them. Just to give an example, there's an amount called 1 mole. And 1 mole of hydrogen gas, what you do is you add up the atomic numbers. You don't have to do this. This is extra. This is optional. Add up the atomic numbers. Hydrogen is 1, H2 is 2. So 2 grams of hydrogen is 1 mole. Oxygen, O2. Well, what you do is you look up there and you see its atomic, actually it's the atomic weight that's important, and that's 16. So this would be 32 grams. And that will also be 1 mole. Now, so this is how you calculate the mole of anything. If TNT, take the chemical formula, add up all the atomic masses, and that's the weight of a mole. The neat thing is, once you have a mole, like for water, H2O, so that's 16, 17, 18. 18 grams of water equals 18 cubic centimeters. 1 mole always has 6 times 10 to the 24th molecules. Or atoms, I guess. Always has that many atoms. I said it wrong. I meant molecules. Okay. Always has that many molecules. So think of it the following way. When you start talking about a few grams of something, now this is what I do want you to remember. This is a calculation you have to do in chemistry classes and physics classes, and I don't want you to need to do that. What I want you to know is that when you talk about things like this, the number of atoms in that, the number of molecules, is something like 10 to a fairly large number, like 10 to the 24. You don't have to remember 10 to the 24. I will be using that many times. So here we have 10 to the 24. How much is in this air? Well, that's like 10 to the 24. How much is in this thing? Well, it's a little bit heavier, so it's probably maybe 10 to the 25. You know, these little details. But it's 10 to the 20-something. So that's a big number. Now, an individual molecule may not have very much energy. In fact, at room temperature, you can see if TK is equal to 300 or so, gee, it's 10 minus 23. Okay, but now you put a lot of molecules together, and you wind up having large amounts of energy, or medium amounts of energy. So the small energy per molecule is compensated by the large number of molecules in anything. Now, this equation relates the temperature to the energy. It's called the absolute scale. It wasn't invented until people knew about absolute zero. And that took a long time to figure out because it's hard to get there. In fact, there's even something called the third law of thermodynamics that says we really cannot ever get to absolute zero. And you'll begin to understand that a little bit more right now. So let's talk about that temperature scale for right now. That temperature really deep down means the energy per molecule. So if here's the energy per molecule, here's the temperature. You know, and here it gets up to 300 when this thing is that number right there, which is, let's see. I didn't put the number there. and so on. This is the energy. It would be that the energy is equal to 2 times 10 to the minus 3, or 600 times 10 to the minus 23. Okay, you certainly don't have to know these numbers. And then as the energy gets lower, the temperature gets lower. When the energy is zero, it gets to zero. Temperature is zero. So that's a nice scale. Historically, there were different scales. Historically, there was the Fahrenheit scale, which right here, somewhat colder than room temperature, was called zero. And everything down there was negative. When you got up to a boiling point of water, which is sort of like 320, 373, that was called 100. So on this scale, I'm sorry, I'm mixing the energy here. I mean, this thing, I should not have put the temperature down here. I should have put the temperature up here. Forgive me for that. So this temperature here was defined as 0 Celsius. This temperature here was defined as 100 Celsius. It was also defined as the boiling point of water as 212 Fahrenheit. Or it is 212 Fahrenheit. And this thing is 32 Fahrenheit. So these are the different scales. But Kelvin is a nice one. There's only Kelvin that goes to 0 at 0. So that's really what we like to use. Now, I call this the hidden kinetic energy because things are moving, but we can't really see them. Well, it turns out you can see them under certain circumstances. Remember, I said that everything is bouncing around and everything has the same energy. So if you have something which is really small, like an atom, it has the same energy that of something that's bigger, like a piece of dust. On the average, they'll all get the same energy. We're not talking about wind where things are moving. We're talking just about the energy of bouncing around. Now, a small atom will be moving at the speed of sound, 1,000 feet per second, 330 meters per second, 1 mile every 5 seconds. That's how fast these molecules are bouncing. They don't go far because they bounce into something and change their direction, but that's how fast they're bouncing around. You get a big dust particle, it's going to have the same energy. But the energy is 1/2 mv squared. And if the mass is much bigger, then the velocity has to be much smaller. So let's make the mass big enough that we can just barely see it. And the velocity will be tiny, but we can still see it in a microscope. So that's what we're going to try to do now, is set up this thing and see. What we have set up here is a microscope. And if you look here on the screen, so if this thing can be projected now, you'll see little dust particles. And they're actually falling slowly. Can you get that screen up there? Is that possible? This monitor. So the dust particles are falling. And as they're falling, because the microscope turns things upside down, and we weren't smart enough to build in the electronics to invert this, they look like they're rising. The red beam is pointing right at my face. I'm trying to eliminate a warp. Okay. That's nothing compared to that. So, do we have that up there yet? Maybe if we turn all the lights out, we can see it better. So these are little particles of dust. All the lights down, and we might be able to see it on the screen. How are we doing? Very slowly. Is there a problem down here? It's not hooked up. Oh, here we are. Look at this. It's not hooked up, I guess. Okay, so he's setting that up. So what you will be seeing, and I'm going to put some smoke particles in there, so you'll see them better. But these particles, which will be rising, that's just because they're really falling in the air. And when I suck in the smoke particles, they may go every which way because there'll be a little bit of turbulence. But the bright particles that you'll see are these little dust particles, smoke particles. When I put the smoke in there, I have a laser beam shining right on them. So that makes them bright. And if you look hard, you may be able to see them flickering around a little bit. This was an effect that was first seen by a biologist named Brown. And he looked at this and drew the obvious conclusion. So as soon as we are on up there, I want you to look at this. His obvious conclusion is that when you look at little things, he was actually looking in water, not in the air. And he saw that little things were bouncing around. They reminded him of paramecium. And he decided the obvious conclusion, little things spontaneously gain life. So take a look at this. And that was his conclusion, that little things are alive. And see how they flicker around and move and bounce? They are falling, but they're bouncing, they're jiggling. That jiggling is now called Brownian motion. Now leave that on. I'm going to try to add a little bit more smoke just to see, just for the fun of it. It's already working and we hardly need more smoke, but hey. So I'll light a match, make the most smoke, I blow out a match. Why do I get smoke when I blow out a match? Interesting question. Suck it in. Well, it's not a whole lot better. You ever think about smoke? What is smoke? So that little jiggling, ground. Now, the understanding of that jiggling was first really understood by Albert Einstein in 1905. And he wrote a paper describing what I just told you. You have the lights on now. It was called The Theory of Brownian Motion. And he was really the first person to demonstrate, to work out the detailed math that showed just how much these particles would move and how they would jiggle and so on. And his paper basically accounted for all the motion that was seen in these particles. Theory of Brownian Motion. It was one of his 3 great papers in 1905. That's why last year was the centennial of Albert Einstein. He wrote 3 papers that year. Brownian motion. It was this Brownian motion that was the definitive paper that basically settled the issue, believe it or not, on whether atoms existed or not. Because the fact that different sized dust particles would bounce different ways, they would bounce less, he was able to explain it this way and predict their motion, made people finally realize that this explanation was the correct one, that atoms really did exist. So think of this. Most of you haven't had children yet. And you will tell your children that you were born, I think most of you are more than 6 years old, you were born in the century in which the question of whether atoms existed was really settled. Not just relativity theory, but even atoms. So this is called Brownian motion. Now, we showed last time, let me give an illustration of Brownian motion here. Let's turn this on. This is just an analogy, of course. You actually saw the real thing. So there, let me turn up the heat. Now the things I want you to notice are, one, the small balls move faster than the large balls. I said this is true for atoms. Why is it true for little ball bearings? It's the same logic. A big thing moving, if something's moving towards a big thing, the big thing doesn't change its velocity much, but the other one bounces off like off a baseball bat with increased velocity. It's only what's going really fast that has a chance of slowing down the big one. So when you mix things together like this, it's the big ones that move the slowest, the small ones move the fastest. This is what we call, sort of, to use a fancy term, we might call this thermal equilibrium. No, you don't have to know that term. This is what happens when you let things sit for a while. You get into the state where the small molecules are moving fast and the big molecules are moving slow, but it's even true for ball bearings. And it's sort of an amazing thing that this happens. But look at that big dust particle there. It's moving slowest of all. In fact, there's enough friction that's not really moving very much at all. When it gets hit, it doesn't even bounce. So let's turn it up a little bit to overcome the friction, get a little bit more speed up here. Now it's bouncing around. And you see that little bit of motion? That's what you are seeing with those dust particles. That little bit of motion, whereas everything else is going, as they used to say, like a bat out of hell. So this is a very nice illustration of the small particles going super fast, the medium-sized particles going medium speed, and the big particles going slowly, but they all have about the same energy. To get energy for a small particle, it has to go very fast. It's 1/2 mv squared. So it makes up for the small m by its large v squared. Absolute zero. At least analogy to absolute zero. Now, these bouncing things put a force on the walls. And if those walls aren't strong enough, and this is hot enough, those walls will move out and you get the explosion. Here's an I don't do this demo, but here's an interesting thought. Suppose I were to take a stick of dynamite right here and explode it right now. The question is, how many people in this room would be killed? Now, I don't recommend you do this experiment at home. Suggested answer? Maybe nobody? What do you say? There's someone else over here raise their hand? Zach, you don't count. You're a teaching assistant. Everyone. Now, somewhere in between. Anyway, the most likely answer is maybe nobody. Exactly right. Why is that? Well, what dynamite does is it explodes, and now you have this air this gas. What happened is the solid turned into gas. So that maybe increases its volume by a factor of 1,000. But more than that, it's a hot gas. Maybe it's 600 Kelvin. That would increase its volume by another factor of 2 because it's going from 300 Kelvin to 400 Kelvin. So maybe it's going up by a factor of 2,000, 3,000, 4,000. Wow, huge increase. Well, a factor of 1,000. That means the stick of the dynamite turns into a gas that's how much bigger? If it's this big in size, then it goes to that big in size. How do you get a factor of 1,000? Well, it's 10 times bigger, 10 times that way, and 10 times that way. 10 times 10 times 10 means 1,000. So when the dynamite explodes, its volume goes up by several thousand, which means its size goes from that to that. That means the air is suddenly pushed out by that much. Now, we haven't talked about waves yet, but that's a hell of a sound wave. That sound will come and hit you in the face and probably break your eardrums. Will it kill you? Usually not. I wouldn't want to be holding it. But if you're standing a few feet away, probably won't do anything more than to break your eardrums. And eardrums, by the way, do grow back most of the time. So you're not going to be deaf for life. We're well designed. I'm not going to get into intelligent design right now. So why is dynamite considered so dangerous? Well, suppose you don't have a stick of dynamite, but you surround it. Suppose we have a little ball of dynamite or other kind of high explosive. And instead of just letting it explode, we surround it with metal. So we put it inside a metal. What is that called? That's called a pipe bomb. Now you have this thing inside where the pressure is suddenly going to go up by a factor of several thousand, and that pipe bomb will shatter. And it will break, and those pieces of metal will then go flying out with this high velocity. And those are what will kill you, not the dynamite itself. Now, with a pipe bomb, it'll shatter. Maybe it'll shatter into 2 pieces, maybe into 10 pieces. They'll go off in some directions, may or may not hit anybody. So now let's get really nasty and mean. Let's start talking about what we would do if we wanted to design an explosive to kill people. Forgive me. I know this is what you don't. This is one of the things people don't like about physics. It's also fascinating to some other people. But let's just try to talk about what it is, because you'll see what people have done in the past. You want to make something that will go out and kill everybody. What you do is, instead of surrounding it with a pipe, let's take a little spear like this. Surround it with metal, but let's make the metal in such a way that it will break up into lots of little pieces. So what we're going to do is make the metal thick, and those are the places where it will break. So each of these pieces will then go flying out when the dynamite explodes. Okay? And if we look at it, this thing will look like this. Now let's put a handle on it so we can throw it. And when we release the handle, that will set off a timer that will make this thing explode and then break into little pieces. And of course, what I've just designed is a hand grenade. And that's why the hand grenade has that shape. It's designed to break up like this. Other thing that terrorists do is they'll take their box of explosives and fill it full of wooden nails. This is awful stuff. But I want you to understand why they do that. The reason is dynamite by itself really doesn't do much damage. It makes a hell of a sound wave, which I'm not going to demonstrate here because I want you to keep your eardrums for the rest of the lecture. But explosives generally require to have, these are like little bullets. How does a gun work? A gun works basically the same way. I mean, you can take a gun and fill it with gunpowder and aim it at somebody and shoot, bang, and that's called a blank. What happens when you do that is here's your gun, which is made of a metal that is strong enough that it doesn't blow itself apart. Now, you put the gunpowder in here, often in the form of a cartridge. So you have this little packet of gunpowder. You put it in the gun, often from above. You slip it in there, and then you ignite it, sometimes just by impact. You ignite it so it explodes. You get this factor of several thousand increase in the volume. If it were closed off, then the metal might actually blow apart. And people whose guns are jammed sometimes have accidents because of that. Especially if you have a lightweight gun, you don't have the extra metal in here. But what you do instead, of course, is put a piece of metal here. It's called the bullet. When this explodes now, it pushes the bullet out. This is the way the explosion goes. The bullet gets to high velocity. That can do damage a mile away. Whereas a blank, that's what they use in movies. The thing explodes. The exploding gases come out. Just a little bit. It's just a gram. It's not like a stick of dynamite. Doesn't even damage your eardrums. It may hurt. We'll shoot a gun here later on. I guess probably next week. I'll have a little gun here that we'll shoot for a momentum experiment. And so that's what's happening. It's an explosion, but it's the explosion accelerating the metal. The metal then having all of its energy. What you're doing is taking heat energy, heat and compressed gas, and turning it into motion, which then can concentrate that energy, in the heart, kill somebody. So it's actually concentrating that energy on getting into the body. It's a way of focusing the energy. All engines are, not all engines, but let's say heat engines. This is a special kind of motor that we're talking about now. A heat engine is a method of taking something which is hot with this random motion going every which way and turning that into some sort of coherent motion all going in the same direction. That's more useful energy. Now, physicists and chemists will make a distinction between different kinds of energy. Heat energy sometimes is the least useful kind of energy. That's because it's so disorganized. Sometimes we say it has high entropy. Entropy is a measure of how disorganized it is. That's a word that's optional in the text. I want you to know a little bit about it. Entropy basically means disorganization. And you can actually measure this. You can put a number on it. Chemists will tell you how much entropy there is in a bottle of water versus a bottle of ice. The ice will have lower entropy because it's solid. It's not shaking as much. Molecules are not moving around as much. A heat engine is something that takes something that's hot with all those molecules. There's lots of energy in there. But it's not useful energy because it's going in random ways. You could use it a little bit if you have it push against a piston. And then the molecule, when it bounces into the piston, pushes the piston, and the molecule will lose some of its energy. And as this piston gets pushed, it's moving away from the molecules. Every molecule that hits it loses a little bit of energy. So you're turning this random motion of molecules into this nice piston motion that you can then use to turn the wheel of an automobile or of a train. And this is called a heat engine. Now, you cannot extract all of the energy of that you have in heat. This random motion cannot be made completely coherent. But that's what heat engines do. This is the heat engine in your automobile. This is a model of it, but it basically shows how it works. And not all of you can see that. Let me move this back. And you may actually see it better on the screen because I can't really face everybody here. But this is a model of what's called a four-stroke automobile engine. And the idea of this is to basically ignite gasoline. The people who work with explosives say you don't actually explode the gasoline. That's because they have a technical definition of what is meant by explode. We often come across people like this, people who have technical definitions and they want to correct you. It really annoys me. They say a buffalo is not a buffalo. It's a bison. Well, where do they get the right to do that? Oh, they're scientists. So scientists have the right to redefine words to mean specific things and then correct you if you don't use the scientific definition. Baloney! Scientists have no such right. An American buffalo is a buffalo because that's what they called it. If they want to classify it as a member of the family of bison and not of the family of buffalo because it isn't related genetically to the buffalo, then they can call it a bison. They can't correct us. I had a math major a nephew of mine, used to correct, I tie a knot, and he'd say, that's not a knot. Why? Because mathematicians decided knots are only things that can't be untied. That's actually the mathematical definition of a knot, something that can't be untied. If you make that definition, you get much more interesting math. So he wanted to impose this on me. I got kind of annoyed at that. No, it's a knot. And a buffalo is a buffalo. And New York City is New York City or New Amsterdam or Constantinople is Istanbul. We name it. We get to name it anything we want. Anyway, but there is a second language called the language of science in which people are more technical. And in that language, the explosion in the automobile is not really an explosion. It is a deflagration. Call it an explosion. Okay, that's in case people are watching this. People are now watching these lectures in Europe and in South Africa and all sorts of places because of the webcast. Oh, by the way, speaking of webcasts, we're now podcast. You can now go to the website and subscribe and put it on your iPod or your computer or whatever, anything you have that accepts podcasts. And that means when working out in the gym, instead of listening to music, you can listen to physics lectures. If that sounds silly to you, it does to me too. You do it while jogging. This is, let's put it this way, a low-cost experiment. It doesn't cost much to send the podcasts, and the university doesn't really know if they're going to be useful or whether you guys will want to listen to these lectures while jogging. So at the end of the semester, we'll ask you whether it proved useful or not, and maybe continue doing it or not continue doing it. The webcasts are certainly valuable because they have the film, and especially if you have an excused absence, you can watch it. So here is our motor now, and we're going to call it an explosion. And the way it works is that gasoline by itself doesn't contain oxygen. So the first thing you have to do is take the gas. So to really make an explosion, you have to do is mix the gas with oxygen. You usually get the oxygen from the air. In a rocket, you have to carry the oxygen with you. But part of the reason fuel works so well is that basically air is free. So you take the gasoline, you break it up into tiny little droplets, and you mix it well with oxygen. And this used to be done in something called a carburetor. Now it's done in something called a fuel injector. But that's what's happening. That process of mixing it with air, getting exactly the right mixture is important. Because if you have too much gasoline, it will burn and won't explode. If you get too little gasoline, it will do neither. Because if one molecule explodes, the heat gets wasted and doesn't ignite the next one. So getting the right mixture is really important. This is why air-fuel explosives are so hard to do. Because you have to get just the right explosion. And so your automobile has really very high technology to getting exactly the right mixture of gasoline and air in order to do this well. The technology is amazing. I mean, it's been developed for 100 years now. And it's exquisite. It makes it very hard to come up with alternative kinds of engines because the gasoline engine is so well done. That doesn't mean your car will start in the morning, but it's based on a lot of tech. So the first thing that happens is you have some sort of fuel injector or carburetor mixing these two. Then it gets sucked into this thing. Let me try to get this right now. Okay, so here we are. The gas is the mixture of gas and air. It comes in over here. This valve is opened, so it will open up. Okay, here it goes, opening up. As it's opening up, this thing moves down, making more room in here. So the high pressure gas, the higher pressure, this thing is sucking it in. Actually, it's the pressure of the gas that's pushing it in, and the cylinder comes down. Okay, so here we are. Valve opens, cylinder comes down, sucking the air in. Next thing, to get the optimum amount of energy out of this, you want to compress the gas. Because this is hooked up to the wheels, and it has a flywheel in there, this thing will continue to rotate and will compress the gas. So you suck it in. The valve is closed. So just watch this again. We open the valve, the gas comes in. Then the valve is closed. These are what your valves are on your car. Close that. They have, you can have valve trouble, leaky valves and things like that. These are where the valves are. Okay, that closes. And now it compresses the gas. When the gas is at the right compression, this is called the compression ratio. The compression ratio is this ratio to this ratio. The more you compress it, the more energy you get out. Very powerful automobiles frequently have larger compression ratios. Larger compression ratios mean you need a bigger, stronger engine to be able to contain the explosion. Anyway, it comes up here and is compressed, and then this thing, especially when I turn it on, so here we go. We suck it in, we compress it, flash, that's called the spark plug. In a so-called diesel engine, there's no spark plug. They use the fact that when you're compressing a gas, you're putting that energy into a much smaller volume. You're actually doing work on it. You're pushing on the molecules. It's like a bat. When the molecule bounces off something that's moving towards it, it picks up energy. So the gas gets so hot that in a diesel engine, it explodes on its own. It doesn't need the spark plug. That's the difference between a diesel and a gasoline engine. So with a diesel engine, you have mainly you have to get this large compression ratio, so you have to have a rather big engine. So they tend to put them on trucks. So it ignites. At this point, the volume doesn't quite increase by a factor of 1,000 because there's already a gas. So it's the heat that increases the pressure. These molecules are moving faster now because they've been ignited. They're broken apart, so there's a little bit more pressure, and that pressure then pushes this thing down and pushes the cylinder down. The process of pushing it down has levers here that then turn the wheels. So it's that 1/4 of the cycle. It's when you're going down that you're getting the energy out of the cylinder. One cylinder engine, very uneven, because you're just getting that energy 1/4 of the time. There's also something called a 2-cycle engine, which doesn't have that same compression cycle, and then you get less energy out, less efficient, but at least you get energy on every full cycle. Here you get it on only 1/4 of the full cycle. Or I guess on a 2-cycle engine, it's 1/2 of every full cycle. Now, the last part, this valve now opens, and that pushes the burnt gas out into the exhaust that goes into the air. Anything that's not burned, not completely burned, gets out. If, some of the carbon in the fuel, the hydrocarbons are hydrogen and carbon. That's why they're called hydrocarbons. The hydrogen is burned to water, H2O. So hydrocarbon consists of a large number of carbons and hydrogens. Methane is CH4, for example. You have C2H6. These are hydrocarbons. The H combines with water to make H2O. The C combines with oxygen to get CO2. There's also some CO, which is called carbon monoxide. Carbon monoxide will actually burn by itself. But this thing happens so fast that sometimes it doesn't completely burn. Outcoming carbon monoxide is bad. It's one of the pollutants that comes out of cars. Another thing that comes out of cars is unburnt carbon. You get simply little particles of carbon. That's called soot. Little unburnt particles of carbon. Soot also comes from a flame here. When I burn this off, some of the particles come out because of the gas that's coming out, but they don't come out completely. Coal consists of the good coal, the best coal, the so-called hard coals or blue coals, consists almost entirely of carbon. Wood consists of carbohydrates, CHs, like these. So when you burn wood, you get some water vapor out. When you burn coal, you don't. Suppose you have some wood and you realize that the water vapor coming out keeps the wood from getting very hot. There's a thing you can do, which is to take your wood and make sure there's not too much air around, so it never gets very hot. Then you can combust it in such a way that just the hydrogen burns and not the wood, not the carbon. And I've seen them doing this in Italy. They bury the wood, bury it with dirt, and then they set it in fire underneath the dirt. It smolders. Smoldering means the carbon is coming out, but it's covered with the dirt, so that carbon is trapped. And the hydrogen is burning. And when you're left, you burn off the hydrogen, and you have only carbon left. Why would you do that? You're wasting energy. Yeah, but carbon will burn hotter than hydrogen. And so now you have something that's called charcoal. This is how you make charcoal. You take wood, you burn off the hydrogen, you're left with the carbon. The value of charcoal is it will burn hotter than wood will. This is why you cook meat on charcoal. It's a hotter flame because it's not using its energy at this low temperature stuff where hydrogen burns, turning into water vapor. So this is the basic engine. There are other kinds of engines. Let me say some more about this. So let's just go over it once more. So the cycle is you suck the gas in, this valve is open, close both valves and compress the gas. When it's at the right compression, you ignite it either by its own heat in a diesel or with a spark plug, and then that explosion pushes this, that pushes the wheel and the flywheel, and then you open this valve and expel the gas, begin the cycle over again. So there you are. So that's the way your automobile works. Your automobile may have 4 of these, may have 6 of them, some of them are 8. A V8 has 8 of these lined in, set up like a V, letter V. So there are all different ways you could design this. Most energy efficient cars have 4. For high power, they have 8. Then there's the hybrid automobile. Now the hybrid is very interesting because today's hybrids have engines just like this. But they have a second system that's designed to store energy. So there are a couple problems with this. One is, as I run this thing, suppose the car is going super duper fast. Then this thing is expanding so rapidly that the explosion doesn't get much to push on it. You have an explosion, but this thing's already moving away fast. The result is when you're going very fast, the engine is less efficient. You have to design the engine for a certain speed. There's a trick about this. When you're going super fast, you go into what's called a higher gear. A higher gear means you actually run the engine a little bit slower than you would otherwise, but it makes the wheel turn more. The idea is always have the engine go at the optimum speed. So when you're in first, you'll start off at slow speed. The engine's going a little bit too slow. It goes faster yet. Then you switch to second gear. Now the engine's going slow, medium, fast. Then you switch to third, slow, medium, fast. So the engine has this limited range in which it works. Meanwhile, the car can be going 5 miles an hour or 50 miles an hour because you're changing how fast the wheels go for a given engine speed. That's called changing the gears. With a hybrid, you could do even better. The idea of the hybrid is you don't have the engine sometimes going slow, sometimes going fast, sometimes going in between. In the hybrid engine, you keep it going at exactly the perfect speed. Now, when you're going slow, you're producing extra energy. So you store that in a battery. When you're going fast, you don't have enough energy. So you take some of the energy away from the battery. So this is the main gain in a hybrid engine. There are two basic ways hybrid energy save energy. But this is the most important one. By keeping the energy moving at its perfect speed so the explosion extracts the most possible energy into the pistons. So, I have a hybrid. The engine is usually either on or off. I come to a stop, and the engine stops. And it starts again. It's kind of weird getting used to. You think the engine is stalled. And no, it's just turned off. And it runs mostly at the same speed. The engine in my hybrid is not perfectly the same speed. It does have some range, but things will get better in the future as hybrids get better and the batteries get bigger. Right now, we're at the beginning of the hybrid era. In 10 years, more than half of you will be driving hybrids. This is a technology that's simply taking over the automobile business. I don't know whether I don't think hydrogen will ever go into automobiles, may go into trucks, but we will all be driving hybrids. It's just so much better than anything else. Okay, now, the other thing that a hybrid can do is when you're going downhill, you don't need energy. In fact, you have to slow down. Traditionally, this is done with brakes. Brakes are things that cause friction. They have something inside of your wheel that the wheel rubs against. They try to make it so it doesn't squeal too much, and it just gets hot. Hot from the friction, the same friction you got earlier today. With a big car going and all the energy going into friction, you can heat up the brakes. That's why you don't want to overdo this. You're on a mountain road and going down, the brakes will get so hot that they actually get weak. They get weak because they're thermally expanding. And the molecules are further apart. And when they're further apart, the forces between them aren't so strong. So they tend to break. So you don't want your brakes to get too hot, which means what do you do when you're going down the road? Well, you put on engine braking, which basically means you run your engine. And now when your engine is trying to speed up, it has to suck on this gas, and that'll slow you down. Very, very inefficient. With a hybrid automobile, what you do is you hook up when you're going downhill, you hook up your wheels to a generator, and instead of turning the energy into friction and heat, you turn the energy into electrical energy in the battery. So these are the two aspects of hybrid engines that make them work. Typically, a hybrid engine has an ordinary gasoline engine optimized for a single speed. It has a battery. The battery is used to store the excess energy when you're going slow, to give the extra energy when you're going fast, and to store energy from when you're going downhill. Now, most people would not buy hybrids that did just that because when they're going fast, they'll have to go fast for a long time on the highway and so on. And so your battery is going to run out. So they do make hybrid engines that will go at different speeds. And so that's why my Prius is rated at only 60 miles per gallon. You could imagine, for example, a hybrid in which all you have is a bigger battery, and you never run off this. All you do is use this just to charge the battery. It would require a bigger battery. Those are kind of expensive these days. Instead of being $20,000, $25,000, it might be $50,000. People aren't going to buy those just yet. But if you do that, you can get the efficiency much greater than 60 miles. By the way, I don't really get 60. I got 50 one time by being very careful. You know, driving 100 miles away and 100 miles back, yeah, I could get 50 if I'm careful. Never to change the speed of the automobile too rapidly. Because it's when you're going slow and fast that this engine can't quite adapt to you like that. So that's what a hybrid engine does, and they are the engine of the future. Let's talk a little bit about this expansion, because a gas will expand. And if you, let's say you keep it under a constant pressure, the atmospheric pressure, 15 pounds per square inch, and you double the temperature. That means from room temperature, which is 300, you go up to 600. By the way, on the centigrade scale, that's just 300 above zero, right? Because room temperature is close to zero. It's not really zero. It's 25 degrees, 26 degrees above zero, but you know, that's pretty close to zero. We live in a very narrow temperature range. So if you double the temperature, go up to about 300, you get about double the pressure. So with 300 degrees, you could say it's expanded by a factor of 2. So basically it's expanding by a factor of 2 every 300 degrees. Most solids don't expand that much. That's because they have strong forces between the molecules. And so when you heat them up, they get a little bit bigger, but a more typical thing is 1 part in 10,000 or so. So this is a rough number I'd like you to know, that you heat up a piece of solid, and it will expand by about 1 part in 10,000. Some things are different, so 1 in 10,000. So what does that mean? That's for 1 degree. 1 degree. I have a discussion of whether, why, old term used to be say 1 degree Celsius. Now we just say 1 Celsius. The word degree, scientists decided that was just confusing. It has nothing to do with angles. And it's an old terminology. So these days, frequently you'll see it written as for 1 Celsius. Now, suppose you have a bridge that's 2 miles long. That's 10,000 feet. So it'll expand by 1/10,000th of that, which is 1 foot. So a bridge that's 2 miles long will expand by 1 foot with just 1 degree temperature change. What about a 10-degree temperature change? 20 feet. That's a lot. So this thing doesn't seem like a lot, but it adds up, and it becomes a serious problem. Sidewalks. When people put down concrete, they know the temperature is going to change, and the sidewalk's going to expand. And all though it's expanding just a little bit, it's pushing right against other concrete, and it'll crack the concrete. So they put in cracks. So the concrete has a place to expand. There are some more insidious places where you do this. The Bay Bridge has these cracks. You can see them when you're driving. Every now and then you come to a place where what they have is the bridge comes like this. You're looking down on the roadway, and you see things like this. And on the other side, you have things that go in between. And they don't do this every 2 miles, because if they did that, the expansion would be several feet, and this would be too large. So they do it every quarter mile or eighth of a mile, something like that. And these things will expand in the heat. And they'll move in and out, and your car will still go over them okay. They look like cattle crossings, but they may put a cover on them that just slips. And these are the expansion joints. But the strange, didn't bring my photo with me these things are called expansion joints. And here's an interesting fact. They're basically pre-cracking it. So the crack's already there. It looks pretty. But it also gives space so that the concrete doesn't suddenly get shoved against other concrete. The forces can be enormous. Because if you imagine something expanding by a foot and ask what forces I put against something, the force is the same as you would get if you took that concrete and compressed it a foot. And you know how much force that'll take. It's enormous. So this thing is naturally a foot longer, but there's no space for it, so it will push at this great speed. This is the same thing that plants use to crack concrete. You know, get a little seed in there, and it starts growing in size, and the forces it generates are enough, and it can crack the concrete. And you've seen this in sidewalks, where a seed coming up between a crack can wedge the concrete apart. Now, there's a photograph, maybe I'll bring it in next time, of the levees in New Orleans. And when you look at the picture of where the levees broke, it's really interesting. You look at it from above, and what you see, well, from the side, the levees had these concrete things in them like this. And they went under the ground, and they were buried. And this was supposed to hold the water. So this is the way the levees worked. They actually had these walls, these buried walls to hold it. It wasn't just dirt. They actually had these walls in there. Now, if you look at it from above, the walls normally go like this. This is looking down on it. After the levees broke in New Orleans, and you look down on it, what you saw was this. Like that. The thing I noticed immediately when looking at this is, wow, these little pieces are all the same length. It wasn't just a random shatter. These pieces broke like doors. And then I realized what it was. If you have a concrete wall and the temperature changes, it will expand and crack. So you have to put in expansion joints. Now, how do you put in expansion joints in something that has to work for a flood? It's not really that hard to do. I mean, an expansion joint might look something like this. With a very good seal put in there. Maybe rubber or something like that. So they have to have expansion joints. Otherwise, the levees would shatter themselves when the temperature changed. By the way, glass. These days, everybody uses low expansion glass. But if you have, there's still some glass which if you heat it and then put it in water, one side cools faster than the other. And that side contracts and this side doesn't, it tends to shatter. You break glass by putting it in from hot to cold water. It's the same thing. So these things are designed like this. Now, this is great because it prevents them from cracking under heating. The problem is this is invariably going to be the weakest part of the levee. And the engineering problem, you must put in expansion joints. How do you design an expansion joint so that it's strong enough? It's going to be the weakest point. If you look at the strength of a levee, it will be the strength of the expansion joints. That's what determines it, not the strength of the concrete. And you've got to have those in there. And in fact, in New Orleans, it is at those expansion joints that the levees broke. So now when you look at these pictures, I'll try to bring them in, you will see something different. You will see the problem that the engineers are up against. It's not an easy thing. What else do I have on the list here today? Altitude. When a gas expands, when this hot gas pushes against this cylinder, it's like you're pulling your baseball bat backwards. And the ball comes in and it loses its energy when it's going against a backwards going baseball bat. Anything that goes against something that's running away from it bounces with less energy. So things cool when they're against something that's receding. This is the basis of refrigerators. It's the basis of heat pumps. Heat pumps was one of the answers on today's quiz. Best way, most efficient way to cool a house or to heat a house is with heat pumps or a refrigerator run backwards. That's in the text. This process of receding, I can even do it here. I could take a gas that's compressed. If it expands, the air is moving away from it. The expanding gas is losing energy, and therefore it's cooling. It will actually cool below room temperature because this gas is the random stuff, but as it bounces against the air that's being pushed out, it's losing energy and expanding. So I should be able to get this thing to lose energy and expand. Let's see. You notice some snow. That snow is not from the carbon dioxide in here. Oh, well, it is. It's expanding carbon dioxide, cooled so much that it froze, and some of the water vapor in the air is also freezing. I really like this thing. This is the basic idea of refrigerators, of all these things, refrigerators and and heat pumps is expanding air. So what you do in a refrigerator is you have a little cylinder inside the refrigerator, not with a spark plug, but a little cylinder inside the refrigerator. What you do is you push gas into it and compress that gas. That heats up the gas. Bad thing. You want a refrigerator. Okay, but you got the room. So what you do is make sure that heated gas is in good contact with the room, and it heats up the room until it reaches room temperature. And it can be designed to do this very quickly. So now you have compressed gas that's at room temperature, and your room has gotten hotter. Now you expand it, and this gas will get cold, just like this thing did. Now you take that cold gas and feed it inside the refrigerator. We actually usually don't take it into the refrigerator. You put it into tubes that go into the walls of the refrigerator. But this will be a cold gas. And you get it by having a motor that first compresses things. That's why you need a motor. Then releases the heat into the room. That's why refrigerators can't cool a room. You wind up releasing more heat into the room than you're going to get cooling inside of the refrigerator. A refrigerator is taking the heat in this gas, moving it into the room, and with the leftover cold gas, using that to cool the refrigerator. So this is used for refrigerators, heat pumps, and other things like that. And it's basically this fact that when you expand a gas, it gets cold. This is an important concept for you to know. What happens if you climb a mountain? You know it gets cold. I go up to Yosemite Valley, and it's typically, 15 degrees cooler. Why? Just because it's higher? The answer is the same. Wind is blowing all over the state. Suppose there's some wind down here, and the wind goes up the mountain. As it goes up the mountain, it will expand because the pressure is less. When it expands, it cools. As a result, when you get up high, it's colder. You go up in an airplane, and the pilot loves to announce the temperature outside is minus 50 degrees Celsius, or something like that. Really, really cold. It's the same thing. It's because we have a very turbulent atmosphere with thunderstorms. Air is moving all over the place. But whenever air gets up to a lower pressure, it tends to expand, and that makes it cooler. One last demo I wanted to show here that I haven't gotten to. Let me just show you this thing, and then we'll call it quits for the week. By the way, get your bios in, and make sure your homework's are due, and you have another reading due next week. Real pace of reading here. Take a look at these things. Can you see them up there? Can you do a close-up on this? This is a really nice thing. It has these little things inside of it, which, when I think about it really hard, and I concentrate, they tend to go down. And if I can make them both go down, actually, by thinking hard enough. And then, if I stop thinking, they start coming up. Unless I want them to go down again, in which case they go down. But then they can come back up. But if I don't want them to come up, they won't. Kind of hard to keep them at exactly the same place because they have their own minds of their own a little bit. They exercise, it seems, free will within a very short range. Mostly they're trying to read my mind. These are called Cartesian divers. Let me very quickly tell you how they work. I'm actually pushing on this. When I push on the water, I push on these things. When I push on these things, they get compressed. When they get compressed, they're mostly full of air. If they get smaller, small enough, so their total weight is less than the weight of the water, they'll float. If it's greater than the weight of the water, they will sink. So this is the key to floating. You have to have the average weight of the object less than that of water. Do some more on this next time. Have a great weekend.